A rare visitor from deep space is in fact racing through our solar system, and it's breaking records on the way. Scientists have confirmed that the third ever interstellar object named 3I Atlas comet is on an extremely unusual path, moving too fast to be bound by the sun's gravity. A new interstellar object like Oumuamua, just spotted entering the solar system at extremely high speed, sparks awe and curiosity across the astronomical community. This rare visitor, designated 3I Atlas, emerged from the depths of space with such velocity and trajectory that it instantly captured the attention of observers worldwide. Detected on July 1st, 2025, by the Atlas Survey Telescope in Chile, the object was already racing toward the inner solar system from a distance of some 4.5 astronomical units. It became known as the third confirmed interstellar interloper, following Oumuamua in 2017 and Comet Borisov in 2019. Please consider liking and subscribing for more updates. From the moment it was recognized as interstellar, 3 Atlas presented itself as a cosmic messenger unlike any other. Its hyperbolic trajectory and extraordinary hyperbolic excess velocity confirmed that it was not bound to the Sun. Its orbital eccentricity of roughly 6.1 dwarfs the already steep values of Oumuamua and Borisov, marking it as the most eccentric interstellar object observed to date. Traveling at tens of kilometers per second, its speed exceeds all prior records. Estimates place its velocity at approximately 130,000 mph, around 210,000 km per hour, a pace that outstrips previous interstellar arrivals. Astronomers scrambled to capture every piece of this extraordinary visitor. The Hubble Space Telescope, working in concert with ground-based observatories, provided remarkably detailed images. On July 21st, for example, Hubble captured a striking view of 3I Atlas, a fuzzy coma with a teardrop-shaped dust envelope enveloping what appeared to be a solid, icy nucleus. Back on Earth, observatories like the Vera C. Rubin Observatory refined estimates of its size, initially estimated at up to 15 kilometers across, later refined to approximately 5 to 10 kilometers. Even modest estimates place it significantly larger than Oumuamua and comparable to or exceeding the size of Borisov. As it journeyed sunward, 3I Atlas began to show classical signs of cometary activity. Outgassing created a coma and distinctive tail, while spectroscopic observations detected water vapor and OHH emissions at approximately 3.5 astronomical units from the Sun, earlier than typical for solar system comets. This behavior is unusual, as most comets only become active at closer solar distances. The presence of water and sublimating icy grains hinted at a volatile, rich composition, possibly shaped by its origin in the thick disk of the Milky Way, where low metallicity environments favor water-rich, heavy, element-poor bodies. By tracing its origin in space, astronomers calculated its galactic velocity components. It was moving away from the galactic center and upward through the galactic plane, a motion characteristic of thick disk objects. Age estimates for 3I Atlas place it between roughly 1 and 10 billion years old, potentially making it older than the solar system itself. If confirmed, this would make it not only the most eccentric and fastest interstellar object known, but also among the oldest ever witnessed. Public fascination intensified when some voices raised alternative theories. Harvard astrophysicist Avi Loeb and colleagues speculated that certain features, such as its unusually bright appearance, large size, lack of detectable typical cometary chemicals early on, and its orbital alignment with the solar system's ecliptic plane could suggest a possibility of an artificial origin, though this remains highly speculative. They advanced the notion that 3I's Atlas might be an extraterrestrial probe, though these hypotheses lack empirical support and are not endorsed by the broader scientific community. Their speculation captured headlines and prompted calls for rigorous study, sparking debate across the scientific community. Nevertheless, many researchers emphasized that all observed behaviors, including water outgassing and classic comet-like activity, are consistent with natural origins, calling the artificial hypothesis premature. Despite speculation, one thing remained clear. Atlas poses no threat to Earth. Its closest approach to our planet will be at a safe distance, about 1.8 astronomical units, far beyond even Mars, and it will never come near enough to endanger us. Its journey brings it close enough to the Sun, reaching perihelion around October 29th or 30th, 2025, to offer a rare observational window from both ground and space before it retreats back into the void. The implications of this discovery stretch into multiple domains. Every interstellar visitor offers a fresh window into the architecture and chemical evolution of other star systems. Oumuamua challenged our understanding of small body physics and hinted at the existence of rocky, inert interstellar wanderers. Borisov revealed a classic cometary profile, rich in materials similar to our own Oort cloud objects, and offered comparative data on composition. Now, 3I Atlas brings new revelations. Its enormous speed, extreme trajectory, possibly ancient age, and volatile behavior at large distances all push the boundaries of current scientific models. In particular, its hyperbolic eccentricity and high velocity reaffirm the fact that some interstellar objects are not lightly perturbed bodies flopping through the solar system, but true runaways unfettered by gravity and immune to capture. Its retrograde, slightly inclined orbit, combined with its thick disk origin, suggests a population of interstellar bodies coming from directions astronomers once thought unlikely, informing future survey techniques and detection strategies. Scientifically, this object offers a one-of-a-kind natural probe. Its composition, consistent with water, ice, and organic rich dust grains, may help link distant star-forming environments to the building blocks of planets. Studying its activity far from the Sun provides a rare test of sublimation physics under cold conditions. Its brightness and size give us an opportunity to study nucleus structure, dust grain ejection, and the physics of cometary tails at scale. Philosophically, observing such a relic, possibly older than the solar system, and born in a different epoch of the Milky Way's history, reminds us of our tiny cosmological context. It invites reflection on the way star systems form and evolve, scatter debris into the galaxy, and occasionally send fragments hurtling across light years to wander into our view. As the comet brightens toward perihelion, global astronomy assets, including the James Webb Space Telescope and ground-based networks, are being marshaled for concerted observations. Though a direct spacecraft interception is logistically and financially improbable, the data we can gather enhances our understanding in meaningful ways. Every pixel in the Hubble imagery, every spectrum captured, every curve in its light signature helps refine models of cometary outgassing, composition, small body aging, and interstellar origins. Intriguingly, its anomalously bright early appearance hints at potential outbursts or fragmentation, as seen in other comets. Whether it fragments, flares, or simply passes smoothly, each behavior harbors clues about its internal structure and resilience after eons of interstellar drift. Importantly, discoveries like 3I Atlas pave the way for future readiness. With more sensitive survey telescopes coming online, astronomers expect to discover dozens of interstellar objects annually. Each arrival builds the statistical sample, helps establish population characteristics, and improves our ability to interpret their life cycles, compositions, and the roles they played in galaxy-wide planetesimal exchange. As 3I Atlas speeds through our solar arena one last time, we stand at the threshold of intense observational opportunity. What we learn in the coming months about its structure, behavior, and origin may shift paradigms just as Oumuamua and Borisov did. This arrival is not the beginning nor the end. It is an invitation for humanity to deepen its gaze, refine its tools, and prepare for the galactic visitors that inevitably continue to arrive. The most captivating chapter of this cosmic saga unfolds not just in what we see, but in how the object transforms before our telescopes. Over the weeks following its discovery, the dust-enshrouded traveler, now bearing the name 3I Atlas, displayed a rhythm of rotation that spoke of an internal heartbeat of sorts. Photometric tracking unexpectedly revealed that it spins every 16 hours with astonishing precision. Its subtle brightness variations, a gentle 0.3 magnitude, hinted at uneven surface features or shifting albedo patterns, whispering clues about its texture and structure. These flickers of light began to tell us that this was not a uniformly smooth body, but one with personality in its rotation. As summer deepened, the object's coloration shifted toward the red, a reddening trend across the coma that grew more pronounced. This evolution suggested fresh layers of dust, or perhaps the unveiling of more processed, irradiated organics on its surface. These changes, subtle yet telling, revealed evolving surface chemistry, perhaps the exposure of deeper material as volatile layers burned off or dust was freshly emitted. Simultaneously, water, particularly in the form of OH vapors, was detected at unexpected distances. The ultraviolet eyes of Swift's observatory captured faint OH emissions that emerged from more than 3 astronomical units away from the Sun, well beyond where water typically escapes comets within our own system. Estimations based on those glow signatures suggested a water production rate that implied at least 19 square kilometers of active surface, impressive for a nucleus whose size is still uncertain. Delving even deeper, the collective data painted a picture of two volatile scenarios shaping its activity. One posits that sublimation from icy grains embedded in the coma, rather than direct nuclear outgassing, could explain the early detection of water. Alternatively, theorists argue that exposure to cosmic radiation may have crafted a thick crust of irradiated organics on its surface, stunting outgassing until deeper layers warmed. Meanwhile, the mere orientation of its trajectory continues to intrigue. It traverses the solar system in a near retrograde path within 5 degrees of the ecliptic, raising the question, is this precise motion a cosmic coincidence or a hint of an underlying dynamic? While many see only gravitational alignment, born of interstellar mechanics, some voices, most notably Avi Loeb's, treat the near perfection of that alignment as suggestive, provocative, even strategic. He proposed theoretical scenarios, such as particle sprays potentially resembling protective mechanisms, though these are not widely supported. His informal assessment ranks this object as moderately speculative but unconfirmed, though these hypotheses lack empirical support and are not endorsed by the broader scientific community. Yet the scientific chorus remains measured, cognizant that its natural behavior, dust-driven reddening, distant water emissions, a rotating nucleus, paints a coherent picture of an ancient comet rather than a technological artifact. Critiques of alternative theories have warned against premature leaps, urging patience as more data arrives. In terms of sheer dimensions, as ever more capable instruments turned their eye, size estimates continued to shrink. Where early numbers soared to 15 kilometers, recalibrations based on new images refined that to approximately 5 to 10 kilometers across. Though still among the most massive interstellar visitors yet captured in our lens. Every new tool brought fresh insight. The cutting-edge Vera C. Rubin Observatory, still in its validation phase, fortuitously captured the object. Its images, rich in depth and clarity, revealed the coma swelling over days, offering meticulous tracking of its expansion and motion. Simultaneously, efforts to extract discoveries from archival surveys turned up early glimpses. Test records showed that the object was already surprisingly active, even in May, when it lay at around 6.4 astronomical units, adding a new layer to the mystery of what triggered its early activity. With each successive day, the comet's visibility evolved. By late summer, as it crept inward, its brightness climbed, whetting the appetites of both professional observatories and backyard astronomers. Though still faint, it became detectable at magnitude 14 to 16, bright enough for long-exposure astrophotographers to capture its ghostly glow trailing through starfields. October promised the crescendo of that visibility, though at the cost of proximity to the sun in the sky. The object would edge into solar conjunction, drifting into the sun's blinding glare and dissolving from view for a time, only to re-emerge later. Perhaps most stirring is its provenance. Its motion through the galaxy, calculated in components, moving it away from the galactic center and upward through the plane, marks it as a traveler from the thick disk, possibly born billions of years ago. Age estimates, refined through statistical modeling, place its origin between 1 and 10 billion years ago, potentially older than the Sun by a margin large enough to seed philosophical reflection. This age evokes scenarios of early Milky Way chemistry, where low metallicity conditions forged bodies under vastly different elemental abundances. To trace a fragment of those earliest times, now marching through our system, speaks to cosmic recycling on a galactic scale. This mosaic of data, speed, spin, color, composition, trajectory, provenance, interconnects in ways that beckon new theories of interstellar population demographics. Astronomers are suddenly challenged to ask what compares to what they have only witnessed in fleeting visits. Does 3I's Atlas belong to a class of icy remnants ejected during the early eras of planet formation? Or is it a survivor of catastrophic processes in distant systems? And how many more revolve unseen, awaiting our detection? The implications ripple beyond planetary science. Each observation helps refine models of planetary system formation, volatile retention, and long-distance survivability. Comparing its behavior to that of Oort cloud comets, and yet seeing deviations like early water vapor emission or the pronounced rotation rate offers an opportunity to test theories of small body thermodynamics under unique conditions. There is also a pervading sense that this event showcases humanity's growing observational prowess. Just 8 years before, Oumuamua's appearance shocked us. 4 years later, Borisov dovetailed with our desire to understand other systems. Now with 3I Atlas, our tools from Hubble to JWST, from Rubin to TESS, are collaborating on a real-time symphony of surveillance. That synergy not only underscores our progress, but prepares us for the day when dozens, perhaps hundreds, of such objects might be discovered annually, turning rarity into a data-rich field. As 3I Atlas approaches its perihelion at approximately 1.36 astronomical units from the Sun around October 29, 2025, every passing hour brings new vantage points. Post-perihelion, we anticipate observations by Mars orbiters, which may glimpse the relic as it passes Mars closely on October 3rd. Jovian missions may observe it in March 2026. Each lens will offer fresh frames. Each dataset feeding our understanding of interstellar matter's response to solar heating, to tidal forces, and to radiation pressure. Beyond the science, these celestial visitors remind us of our place in the universe. Their silent arcs tell of detachment from stellar systems, of ejection by unknown cosmic dramas, and of endurance across epochs. In that tale, we, a species perched on a comparatively young planet, catch a transient glimpse of objects that predate our star and whose paths stretch uninterrupted across light years and lifetimes. In the brief months that 3I Atlas graces our sky, we harness our best technologies to capture whispers of its journey. Telescope time, computational models, spectroscopy, astrophotography, all converge to grade our comprehension of the cosmos. If this interstellar traveler teaches us anything, it is that even the fleeting can shape ambition to watch, to record, to understand not just where we are, but how far our gaze can reach in both space and time. From the earliest days after discovery, spectroscopic analyses began to peel back layers of mystery with each passing wavelength. Observations with the SOAR telescope in Chile, under a crisp southern sky, revealed a reflectance spectrum colored by subtle red shifts, hues evocative of distant trans-Neptunian objects, coupled with a slight UV optical turnover that spoke of complex carbon compounds and irradiated organics thriving in cold, far-off environments. Yet none of the usual cometary gases, CN, C2, CO, or OI, were detected at that time, reinforcing the mystery of how activity was taking place without conventional drivers. In a companion sweep of photometry and spectroscopy during July, a team spanning multiple hemispheres recorded the spin rhythm of the interstellar traveler, a period of just over 16 hours paired with a light curve amplitude of around zero point 0.3 magnitudes. These metrics, combined with an observed gradual reddening and growing dust activity, frame the object as a faintly active outer solar system-like comet, just viewed in this case from elsewhere entirely. Meanwhile, Hubble's powerful gaze returned with numerical depth. In a precise study of its inner coma, astronomers derived a dust mass loss rate that varied with the size of particles, anywhere between 6 and 60 gigaosis depending on grain size. This estimate came hand in hand with a tightly constrained nucleus radius, no more than 2.8 kilometers if we assume a reddish albedo, yet not smaller than 60 meters if the sublimation was driven by carbon monoxide. At the same time, ultraviolet imagery from the Swift Observatory added fresh texture to the portrait. Around late July to early August, observations captured OH emission near 385O hydroxyl signatures that betray water sublimation. Calculations from these emissions indicated a water production rate of roughly 1.35 plus 0.27 1027 molecules per second, or about 40 kilokicus. That, in turn, suggests an active surface area of at least 19 km², meaning that a substantial fraction of the surface must be energetically releasing water. In fact, if the nucleus radius is toward the smaller end of estimates, over 20% of its surface must be active, far more than typical solar system comets. Observations also signaled that this water release may originate not solely from the nucleus, but from icy grains within the coma itself, a dynamic that might help explain the earlier onset of activity at distances where sunlight should otherwise be too feeble. In parallel, visual measurements from Japan's Subaru 8.2 cm telescope brought chromatic clarity. 3.Atlas emerged as extremely red, its color matching or exceeding that of D-type asteroids, dark organic-rich bodies commonly found in the outer solar system. Yet again, no rapid fluctuations in brightness were seen, reinforcing the smoothness of its rotation and the lack of any dramatic outbursts. Layered into these natural observations is a provocative narrative seeded by someone who straddles science and speculation. Avi Loeb, observing the finely tuned trajectory of 3.Atlas, so almost perfectly aligned with the solar system's planetary plane, and noting the forward glow anomaly, proposed hypotheses that reached beyond comets. He proposed theoretical scenarios, such as particle sprays, potentially resembling protective mechanisms, though these are not widely supported. His informal assessment ranks this object from moderately speculative but unconfirmed, though these hypotheses lack empirical support and are not endorsed by the broader scientific community. Adding contextual weight, Loeb has considered whether we should even attempt to message the object, a kind of cosmic blind date. drawing on analogies to past radio broadcasts aimed at distant stars. He argues that waiting until after perihelion, when a natural comet would flare, might be prudent. If the object behaves unusually, that might push its artificial likelihood upward and perhaps justify an outreach across the interstellar void. While these ideas remain speculative, they underscore the emotional gravity of the moment. Science, once the sole inhabitant of the discussion, now shares the stage with philosophy, with the social excitement of contact, with political suggestion. Even a congresswoman has weighed in, recommending that NASA consider deploying Juno for a flyby study, a gesture as human as it is bold. Still, within the measured corridors of scientific consensus, the focus remains on observation. With perihelion approaching and 3I Atlas set to disappear behind the Sun in late October before re-emerging in December, every data point now is timed, urgent, precious. As NASA and other agencies prepare, colleagues across the globe anticipate leveraging the James Webb Space Telescope, Mars orbiters, and ground-based telescopes in tandem with an eye to resolving composition, dynamical stability, and the very nature of the outgassing mechanisms. Its trajectory also continues to fascinate those charting its path. Inclined at about 175 degrees to the ecliptic and retrograde, its journey will sweep it close to Mars in October, pass Earth at a safe distance past perihelion, and drift near Jupiter by March of 2026. This cosmic choreography invites observation across distances not usually covered in a single arc. Meanwhile, estimates of its age, based on galactic orbit tracing, anchor it in antiquity, likely hailing from the Milky Way's thick disk. It may be billions of years older than the solar system itself. Such a provenance raises existential questions. Could chemistry from our galaxy's youth survive intact until now? How did it endure galactic radiation, collisions, and eons of drift? Each fragment of data about 3I Atlas is more than a number. It is a whisper from another corner of time and space, beckoning us to listen. Its dust grain emission rates, its surface activity, its color, its silence and molecular signatures, they are brushstrokes in a portrait painted across light years. Yet its passage also exemplifies our progress. Instruments like Hubble, Swift, SOAR, Subaru, Rubin Observatory, and soon JWST are each contributing a layer to the narrative. Where once interstellar visitors were glimpsed in fleeting shadows, now they can be studied across spectra and time. Perhaps most important is what it says about preparedness. In the not-too-distant future, such objects may become common commerce in our surveys. Each visit will build the statistical sample, each data point offering new insight into the formation of stars, the makeup of planetesimal belts, and the distribution of water and organics beyond our system. By mid-August, the faint trail of dust sweeping away from 3I Atlas had taken on a more complex architecture than first glimpsed. High-resolution imaging from the Lowell Discovery Telescope hinted at subtle asymmetries in the tail's curvature, suggesting that the object's emission was not purely isotropic. This uneven release of material could be tied to localized regions on the nucleus, possibly